Hello.
Yeah, that's it's fine. All right, I think we're ready to roll. Okay, everyone, if you can sit down. Sorry.
If you have a copy.
What time did we say we start?
4 or 5.
We said 4 o'clock. Give it 2 minutes. Well, people can come in late, doesn't matter. We'll ask so many questions that you're using to line up anyway. So we're really very delighted to have Vedika Khemani here this afternoon. Vedika works on non-equilibrium quantum dynamics. She did her PhD actually with Shivaji Sondhi, but in the days when he was over at Princeton. And recently she's been a faculty member at Stanford University. I guess I should also mention she got the New Horizon Prize in New Horizon Breakthrough Prize recently for her work in this area, and she worked on things like time crystals. And we're really interested to hear her work this afternoon on topological spin glass order. So welcome.
Okay, yeah, thanks very much, Piers, for the kind invitation and the introduction.
1 hour, 20 minutes, but
Yes.
stop at least 10 minutes before the end.
Okay, and please interrupt and ask questions. It's really wonderful to be here. I'm really excited today to tell you about an area of work that's very, very new to me. It's going to be on this striking new phase of matter called a topological quantum spin glass. This is going to connect various themes of this conference. This will certainly be unconventional. It will be topological. It will be dynamical. Quantum materials depends on how generously you allow me to call different things quantum materials, but okay. So as the name suggests, this phase, topological quantum spin glass, is going to combine the properties of the physics. It's going to combine the physics of topological order with the physics of spin glasses. Okay, and these two phenomena, of course, separately have been at the center of many breakthroughs in many body physics over the last 50 years. They both lie outside Landau's paradigm for phase classification. And the interesting thing about this phase is that both these features are going to play an important role. Okay, this work will also have connections not just to this interesting phase of matter, but also to quantum information. In particular, it will furnish a mechanism for creating a quantum memory, and it will describe the physics of certain new families of error-correcting codes, which have been discovered in the last few years, which I'll tell you about. Okay, so since this is quite a bit different from various of the talks in this conference, I just want to start by telling you what I'm going to tell you and to place it within a broader context. So broadly, an overarching theme of my talk is going to be connections between the fields of many-body physics or condensed matter, the topic of this conference, and the study of information and computation. Okay, and this field, this thing that I'll tell you about is going to very intrinsically talk about. I'm going to talk about both aspects of this phenomena. Okay, so what am I going to show you? I'm going to tell you that this is this phase of matter, many-body phase, combining features of spin glasses and topological order. The thing that's going to be very new relative to spin glasses that we're more familiar with is that there's going to be robust quantum entanglement and quantum memories also at finite temperatures. Okay, so usually in many familiar cases, entanglement is more operational, more important at 0 temperature. Here it's going to play an important role at finite temperatures. This phase, as I mentioned, is going to be realized in certain new families of error-correcting codes. So it's going to give us a new physical mechanism for obtaining quantum memory. I'll explain to you what that means. But what I found very interesting is even forgetting about these new quantum error-correcting codes and just going back to this vast literature that exists on classical spin glasses, by making this connection, we were actually able to take tools from coding theory, which are very transparent, actually. They're very, very simple algebraic tools, which I'll tell you about. But by using those, we were able to give a new, very physically transparent approach for proving spin glass order and features of energy landscapes, even in models of classical spin glasses, which have been around for a very long time. Okay, so this allowed us also to find new families of classical spin glasses and to give a different approach to things like replica symmetry breaking or cavity method, which people have relied on for a while, but which can be, at least to me, was quite challenging, and the physical pictures for the phenomena is much more opaque in that language. Here I'll give you a different approach for deriving those features. And I won't talk about this at all, but I just want to flag it. We prove what's called a bottleneck theorem for quantum channels. This was kind of a necessary technical step for us to formulate this phase and prove that it exists. In the classical context, there is a lot of work on Markov chain bottleneck theorems that people have studied in statistical mechanics. This has been a very fruitful area. We prove a quantum version of this. This gives us a perspective on formulating phases of matter, robust phases of matter at finite temperature, and also has some consequences on the performance of quantum algorithms. One of the things you might want to do on a quantum computer is to prepare something like a Gibbs state at some temperature. And this theorem that we prove is going to give you some bounds on how fast or how well the quantum computer can do that. Okay, so those are the themes: new phase of matter, new error correcting codes, quantum channels. But now I'll dive in, and I can't do that before acknowledging the people who actually did the work. Most of the work I'll tell you about has been published or put in the archive in these two papers late last year. There's another that's in preparation that should be posted soon. And I really want to particularly acknowledge Benedikt Placher, who's a postdoc at Oxford, and Tibor Rakowski, who was a postdoc at Stanford and is now a faculty member in Budapest. Okay. So stepping back, as I said, overarching theme is going to be this relationship between many-body physics and information and computation. Condensed matter physics, as we all know, is the study of the emergent properties of systems of many, many degrees of freedom. Traditionally, this is focused on discovering and understanding phenomena that exist in materials in nature. But starting about 20 years or so ago, this field was reimagined or revolutionized or revitalized by various ideas from information theory, quantum information. For instance, things like quantum entanglement, tensor networks, quantum circuits, which have had a big impact in how we characterize and classify ordered states of matter, how we understand their properties, and also in thinking about order parameters for new types of phases of matter, which may not exist in natural materials in nature. Okay, so this has been a very, very productive direction over the last 20, 25 years. But in turn, of course, ordered phases of matter have also played a crucial role in the field of information and computation. One specific example that I'll talk about today is in the development of error correcting codes. And this is because ordered phases of matter furnish a natural physical mechanism to robustly encode information in the types of ordered states that exist in some non-trivial phase of matter. Okay. A very familiar example from our classical world is a magnetic hard drive. Okay. In a magnetic hard drive, we want to robustly store classical bits, zeros and ones. If we associate these classical bits with the ordered states of a ferromagnet, okay, so the globally up ordered state is associated with 1, the globally down state is associated with 0, and because this classical information is encoded in global magnetization patterns, even if you have some small number of local bit flips due to thermal noise, you can still robustly recover your data. Okay, so this is bit flip error and robustness. And of course, how we would get this ordered up and ordered down states of this magnet is due to symmetry breaking order. Okay. On the other hand, if we have quantum bits or qubits, then we need to protect not just whether the qubit is 0 or 1, but we need to protect all of these coherent superpositions of this qubit state. So the state that I want to encode is what I'll call a logical qubit. And now we need something fundamentally different. We need a new mechanism because we need to protect this logical qubit, not just against these types of errors that flip the bits, but also against phase errors, which may destroy this coherence. Okay, and this new mechanism that was realized by Kitaev, which ends up being extremely powerful, is to actually use topological order to encode logical qubits. Okay, so you take an entangled state of many, many physical qubits. Okay, that entangled state is going to represent the logical state of some one logical qubit. And the reason for using topologically ordered states of matter is that these topologically ordered states are all going to be locally indistinguishable from each other, but different topologically ordered states, different states are just going to differ by some global patterns or global entanglement structures. So if you have your system, which is subject to local noise, okay, whether it's local bit flip noise or local phase noise, as long as the information is encoded in some global topological entangled degrees of freedom, then it can be protected robustly to this local noise. Okay, so the same feature of local indistinguishability, which is a hallmark of topological order, also gives you protection it also gives you a mechanism to protect quantum information or a logical qubit. Okay, so just to mention this in a little bit more detail. Second, keep an eye on time. Yeah, just to talk about this in slightly more detail. You know, the canonical, the Ising model of error correction is Kitaev's toric code. This is a model in physics we often study. We always like to study solvable models, zero correlation length fixed points. This is a model where if you're thinking about things as codes, okay, these codes are code words of the code, the things that will encode the logical qubits. Those are specified as a constraint satisfying problem. Okay, you have a set of checks that need to be happy. So in the toric code, I have physical qubits which live on the edges of a square lattice. The square lattice has periodic boundary conditions. It's a torus, hence the toric code. From all of these n physical degrees of freedom, which live on the edges, the system encodes two logical qubits. Okay, the two logical qubits you should think about as coming from the two holes of the torus, the two non-trivial holes of the torus. How do I know that I have two logical qubits? Well, because I'm going to specify my code as the set of states that satisfy a set of commuting checks. These commuting checks are made up of ZZZZ type terms on plaquettes and XXXX terms on vertices, okay? And my code words are the simultaneous +1 eigenstates of all of these local checks. Now, if you specify all of these local checks and you make them all happy, there are still two global degrees of freedom that are left unspecified. Those are these operators which are drawn. These are supposed to wind around the torus. These are what are going to form the X and Z operators of my logical qubits. So I have four ground states or four states that make these checks happy. And these are spin liquid states. This is also a model of a spin liquid. These states are all locally indistinguishable from one another. When written in a local basis, they look like what's called a loop soup. Okay, there's going to be many, many terms in the superposition. This is an entangled state, and it's going to have all of these possible closed loop configurations. And these different states are distinguished by the action of these winding operators, which create an extra non-contractible loop in either direction relative to this first state. Okay, so this state here can be thought of as the +Z or ZZ being up eigenstate of this logical qubit. Then you act with the logical X operator to flip one of the logical qubits, and that gives you this other state. And then this is up down, and this is down down. Okay, and crucially, as I was mentioning, all of these states are locally indistinguishable. So even though, so that, you know, these logical states, it's very hard to make logical errors because that requires you to make this very global operation. Okay. So these are code words. Four code words give me two logical qubits parameterized in that way. But yeah.
So term first on the right, of like the up and the down.
Yeah.
There's one that is like two, but has a loop that goes from like left to right, but there's a pair. Is that
This one?
Yeah.
Yeah.
Does it sort of cancel each other out?
Exactly. So the only thing that's non-trivial is the parity. It's like, is there an odd number or an even number of non-contractible loops around every hole? So this has even, this is odd, this is even, this is odd, even, odd, and then odd. Yeah. Okay. Now, the toric code is a code, but it's also a very, very well-studied model of topological order in physics. Okay, this is a phase diagram of the Z2 gauge theory. This is a phase diagram from this paper by Fradkin and Schenker in 1979. Okay. In this phase diagram, we know that there is what's called a topological phase or a deconfined phase. This is Z2 gauge theory in 2 dimensions. This is also a spin liquid phase, which has come up many times in this conference. Okay, and then there are some trivial phases. Okay, throughout this topological or deconfined phase, we have a robust ground state degeneracy. There's going to be 4 ground states, which are exponentially close to each other in energy, separated by a gap. Okay, this phase has deconfined anyonic excitations. So you have degrees of freedom, which are bosons, fermions, and then they have mutual braiding statistics. And once created, these excitations can be separated without any further cost. Okay, and if you want to characterize this phase, there is a solvable point, the zero correlation then fixed point of this phase, which is exactly the toric code Hamiltonian. Okay, so these code words that I wrote earlier, there's 2 more of them. The code words are the ground states, because in the ground states, you're going to make both of these terms, the AV terms, which are the vertex terms, the BPs, which are the plaquettes. You'll make all terms happy. Okay, and those are the ground states. And there's 4 different ground states in the problem. And now, even as you perturb away, because the phase is topologically ordered, we know that the topological order is going to be robust, again, because of this local indistinguishability property. Okay, so to put it together, what I've told you so far is that ordered phases of matter give you a very natural way to robustly protect information. The 2 paradigmatic classes of ordered phases of matter, which we're all familiar with, are spontaneous symmetry breaking and topological order. And these 2, in turn, form canonical models to protect classical and quantum information. If I have an Ising magnet within the symmetry broken phase, this gives me a classical memory as a code. This is also called the repetition code, because you take a 0 bit and you write it as 0, 0, 0, 0, 0, and you take a 1 bit and you write it as 1, 1, 1, 1, 1. Those are the 2 ground states of the Ising magnet. Likewise, if you have a topologically ordered phase, which is the example that I told you was Z2 gauge theory, which in more modern language, which maybe some of you are familiar with, is actually also understood as a type of spontaneous symmetry breaking, but of what are called higher form symmetries. These are these deformable symmetries. If you're not familiar with that language, don't worry about it. But this topological order, due to local indistinguishability and entanglement, gives me a way to encode quantum memory, and the canonical example of that is the toric code. Okay, yeah.
Is it possible to have higher form classical symmetries?
Great question. Let me come back to that. That's something we're actually thinking about. Yeah. Short answer is yes. What makes it quantum is this thing that people call an anomaly, where you have higher form X and higher form Z, and then they have this non-trivial commutation with each other, which is the line-like operator in this direction and the line-like operator in this direction, both of which are floppy. But you can imagine having, like, if you think of a 3D Z2 gauge theory, you can have just the X-type deformable, or sorry, just one of those types of deformable floppy symmetries without the other, and then that would be classical. Yeah. Good. All right. So these types of symmetry breaking orders, what they give us is a spectrum of my Hamiltonian, where in the classes that I'm considering, where I have a non-trivial ground state degeneracy. We're going to call that ground state degeneracy. We're going to say there's 2 to the k different ground states, okay, separated by a gap. These ground states are either degenerate or exponentially close to each other. Okay, to go from one ground state to another, you have to act with this macroscopic symmetry operator. Like to go from the all up state to the Ising magnet to the all down state, I have to act with the Ising spin flip symmetry. To go from one of these toric code ground states to another, I have to act with this winding operator, which is also this deformable symmetry. So to connect between these different states, I have to act with operators, which are the symmetry operators, which act on macroscopically many numbers of bits or qubits. Okay, so this defines for you what's called a distance, code distance D, which is telling you how different are your different code words. You want them to be very, very different, because if they're very, very different and they represent states of your logical qubit, then the more different they are, the more robustly your information is protected. Okay. So this is how ordered phases give us this type of spectrum. And on the coding side, what you say is that the states of k logical qubits can be encoded into n physical bits or qubits. N is your system size, and 2 to the k is your ground state degeneracy. Okay. And the really amazing thing about error correction, the power of error correction, comes from this theorem called the threshold theorem. This is a type of phase transition in its own right, but it's a non-equilibrium phase transition having to do with whether or not you can robustly protect information in the presence of noise. And what this tells you is that you have some error rate on your physical qubits. Okay, I'm going to call that P. Okay, so this is the rate at which there's some noise that's happening that's flipping a bit or making some kind of phase error. Now, there's a logical error rate, which is how likely is it for your logical bit to flip, not your physical bits. Okay, and this logical error rate has a particular scaling, which looks like P over PC to the code distance. And this is something that diverges with system size. Okay, so what this tells you is that as long as your physical error rate is less than some critical value, then your logical error rate goes to 0 in the infinite size limit. So it's kind of remarkable because it's telling you have these crappy physical qubits or crappy physical bits, but by entangling more and more crappy physical qubits, you make a better and better logical qubit. Okay, and this asymptotically you make a perfect logical qubit. And even though this was formulated many decades ago, the experimental demonstration of this was Google's breakthrough experiment late last year, where they finally showed that this logical error rate scales down as the system size is increased. Okay. Yeah. Yeah.
You don't need to have a gap to protect spontaneous symmetry, right? Is there? You can break continuous symmetry.
Yeah. So these are.
Is there something analogous?
No, so I don't know of that. I mean, the codes that I'm familiar with are all derived from gapped phases of matter, zero correlation length. You're absolutely right that we have this much wider class of phases of matter. Can we use that in more interesting ways for coding? I don't know. I don't know. Yeah, these are the standard codes. Yeah.
Perhaps it's a related question.
Yeah.
So naively, one could think that the reason there are thresholds is that the state space grows exponentially when the number of error channels only grows with this system size rather than the size of the state space. But this seems to, the way you're setting this up, it seems to say that no, there's something more fundamentally topological about the ability to have a threshold. Can you comment on that?
There is something more topological because you are asking about, like, you have to make a very correlated error on d qubits in order to go from one logical state to another. And if you just have random independent errors, then the chances that you will make this correlated Wilson loop operator that makes this logical error is exponentially suppressed in D.
That's this particular code.
Yes.
Topology in order to get
the
threshold. Is topology is that sort of topology?
So what I think the essential feature that I need is local indistinguishability. That I need to act with some big thing in order to go from one state to another. That seems essential. Yeah.
Okay, it's not along the same line.
Yeah.
But all known quantum known DPC codes.
Yeah.
Are they actually?
Very good. Let me come to that. In a moment. Good. Okay. All right. I'm now having to speed up. Okay. All right. So yeah, these phases of matter. Now we're going to come to the last clause of the title of this workshop, right? These phases of matter were, of course, inspired by thinking about materials in nature. The types of models that I'm going to talk about are relevant to a very different class of system. You can call them synthetic quantum materials if you want. But, this is a video from an experiment in a neutral atom system in Misha Lukin's group at Harvard, and he has an incredible amount of control. These are individual atoms which he can pick up, move, get them to interact in controlled ways according to rules of his choice. Of course, as we heard about in the last talk, a big goal of these synthetic quantum devices or quantum simulators is to try to understand properties about these rocks in nature. But my perspective has also been that, well, this is generating for us a fundamentally new regime in which many interacting degrees of freedom are coming together. So we should just directly ask about emergent quantum phenomena in the settings, in the new settings that are opened up by these new types of synthetic experiments. Okay, so there's a wide variety of experiments, and a key defining feature about them is control. They give us exquisite control over individual quantum entities, over their interactions, over their dynamics, and even over their geometry. Okay, so in the models that I'll tell you about right now, geometry is going to play a big role. In fact, I'm going to be working on these weird non-Euclidean graphs. Okay, but experiments can do this. Okay, this is going to be interesting theoretically, but it's also something that's accessible experimentally using either cavity-mediated non-local interactions like Monica Schleier-Smith does, or even just superconducting qubits arranged in different geometries, or these kinds of neutral atom models where you can like actually pick things up and get them to interact again according to geometries of your choice. Okay, so this I think is a vast new frontier for many-body physics, where we think about phases of matter, but with control over their dynamics, or characterized by their dynamics, and with control over geometry. Okay, so in this phase that I'm going to now turn to telling you about, these two aspects, one is non-equilibrium and the second is non-Euclidean. Both of these aspects are going to come together in defining this phase. Okay, so the motivation for why we started thinking about this is in trying to understand a recent breakthrough in error correction. This breakthrough was the discovery of what are called good quantum LDPC codes. Okay, so that's a mouthful. LDPC stands for low density parity check. Okay, this is a generalized kind of locality to a physicist. Okay, a check is just an interaction term. I told you about the toric code that had 4-body X checks and 4-body Z checks. LDPC tells you that every check acts on only finitely many qubits. This is what you would want. And also, this isn't kind of all-to-all in the sense of SYK models where every qubit interacts with every other. But here, it's also true that each qubit is only part of finitely many checks and only talks to finitely many other qubits. Okay, so this has locality, the generalized kind of locality on a graph. Okay, a code is characterized by this triplet of 3 integers, which I told you about. N is the physical system size. K is the number of logical bits or qubits. It's log of the ground state degeneracy. And D, which is the code distance, is how macroscopically different are those different ground states. So you want to make K as big as possible, okay, because that's low overhead. You want to jam in as many logical qubits as possible for a fixed number of physical qubits. And you want to make D as big as possible, because if your logical states are the more different they are, the more robust they are, right? So you want to boost these up as much as you can. As far as scaling goes, K and D can, of course, be no bigger than proportional to N. So the optimal scaling is K and D both proportional to N. Okay, so good is a little bit of a euphemism. This is as good as it gets. Okay, and you would really like this to be true, but it turns out that there's theorems which tell you that you cannot achieve this scaling in any local model on any Euclidean normal lattice geometry. Okay, so we fundamentally need a non-Euclidean expander graph. I'll tell you what that is in a moment to achieve this type of scaling. Okay, I mentioned here that good classical codes have been around for many, many decades, actually starting in the PhD work of Robert Gallagher in 1960s. Then it was forgotten for many decades, and it was rediscovered in 1993. But the quantum counterparts, quantum codes that satisfy the scaling, were only discovered 2 or 3 years ago. Okay, in the early 2020s. So this is a very recent phenomenon. And again, I want to contrast this scaling with what we just saw in the toric code, where K was 2 or order 1, and D, the code distance, was 1 linear dimension of the square, so it was square root of N. Okay, so this is much, much weaker than this, but it turns out that this scaling for the 2D toric code is actually optimal. It's the best scaling that you can get in 2D. Okay, so the models we're going to be thinking about live on these expander graphs. Okay, an expander graph is a graph in which the bulk to boundary ratio, very informally, is proportional. Okay, so you can cut out any chunk of n sites, and then you ask how big is the neighborhood of that chunk, and that neighborhood will be proportional to the volume. Okay, so the boundary and bulk will be proportional. Many of these models, they don't have to, but many of these models have this kind of locally tree-like structure. Okay, so on a tree, we know that as you go out, the bulk and the boundary scales proportionally. But then what this wispy lines are supposed to tell you is that this is a tree, but the boundary of the tree is closed. If it wasn't closed, then you would have these leaves, and the leaves would not obey this property of the boundary and bulk scaling proportionally, because I could take some large number of leaves, and those would not have very many neighbors. Okay, so this is a closed graph, which has this boundary to bulk property. And the models I'll think about, roughly speaking, the actual constructions are fairly complicated. These papers were written by computer scientists. They don't really look like nice physics models, but morally, these models look like generalized Ising models. Okay, so you can put down bits on all the edges of your graph, and you'll put down interactions on the vertices, and the interactions will involve subsets of the bits that enter the vertex. Okay, so I could have like 4 body Ising interactions, and I could have many groups of 4 body Ising interactions that act on these 7 bits that enter that vertex. Okay, I drew these as locally tree-like geometries, but another type of non-Euclidean geometry that's of interest in many different contexts is this kind of hyperbolic tessellation. Okay, in this hyperbolic tessellation, you have lots and lots of small loops, but this also has the property, and again, things are closed in the boundary, and this again has the property of boundaries and bulks scaling similarly.
You say how the boundaries closed, because it means the local geometry is changing at some point on some landscapes, changed from being a tree to the.
Oh, no. So every point looks the same as any other point. So if you were to zoom in on this point, okay, I could make that point the root, and it would look like, and it could look, so there's something called I think it's called an involution radius or something, but basically up to some radius, which is like log n, any point looks the same as any other point, and that's the reason for closing up those boundaries, so that once you close them up, then there's no difference between these points. So a random regular graph is a standard way to get an expander graph. These hyperbolic tessellations, there's a different way to construct them. You can also look at Cayley graphs of non-abelian groups. That's another way to construct them. So there's random and non-random constructions of these types of expander graphs.
What do you use to connect things up at the boundary?
What rules do I use? Okay, so it's not so important. There's lots of, a random regular graph will do it for you. If you have Cayley graphs of non-abelian groups, then there's some group structure which tells you like how things like, it's like if you have translation symmetry, like if you have a 1D line, to generate a 1D line, you can talk about the group where you have one group element where you move forward. But then to make it periodic boundary conditions, you identify and say like n translations is going to bring me back to myself. So there's a
There is a rule.
There are rules. There are very
the way that every single site is equivalent.
Exactly. There are rules. The rules are much simpler to state for random graphs. A random regular graph, regular just means fixed degree, is an expander graph with very, very high probability. So there are rules for constructing random instantiations of these graphs, and then there are also rules for constructing what are called explicit instantiations of these, and the explicit ones are non-random, generated from some group. But they look locally the same everywhere. So that's why there's going to be a sense in which I can take a thermodynamic limit, because I may not be able to change system size by one system. I may not be able to go in a sequence of sizes, which is like 17, 18, 19, 20. It may have to bounce around, but locally, there is a family of increasing n, and locally, every member of that family looks the same. So those are the features I will use. Yeah.
There are no loops in your graph. They are all that's operates.
Oh, good. So I'm going to get to you're jumping ahead to the next slide. So one is, there are these very long loops on my graph, okay, around the edge. This one actually has small loops, okay, but this is not, okay, but let's just think about these for a moment, okay, but obviously you don't want your big loop to be the size of the system. That's a log n size loop. So I want the code to be LDPC. So you're right, like how do I make my plaquette operators? I am going to be taking the thermodynamic limit, but here I'm just talking about classical LDPC codes. So if I'm talking about classical LDPC codes, there are no X and Z type checks. this is like an Ising model, a generalized Ising model. So I'm only putting down classical ZZZ checks on different vertices. Okay. Now to build quantum codes, I need extra structure. I need there to be commuting X and Z type checks. To do that, I need to build up what's mathematically called a higher dimensional expander graph. Okay. And exactly how to do this is not at all obvious. That's why there was this, 40-year gap or 60-year gap, depending on how you count, between classical and quantum LDPC codes. But morally, what you're doing is you're taking one of these crazy expander graphs, you're taking another one of them, and you're combining them in a way that gives you a higher dimensional expander, where locally there are things which look like these pages of a book, lots of local plaquette-like terms. Okay, morally, what you're doing via a formal thing, there's formal product constructions that are known, where you can imagine taking a circle, okay, and if you take the Cartesian product of two circles, you can use that to build up a torus, okay. This is like the expander graph version of that. Okay, so first there's a way to understand this using homology theory and chain complexes. I can talk for another hour about that, but let me not do that. So you build up this graph, which has a certain structure. It has all of these small plaquettes, and then we're going to put a quantum code on it, which means I'm going to need to put both X-type checks and Z-type checks, and they have to commute with each other. Okay, so this can be viewed as some kind of generalized toric code. Okay, so now we come to the question that someone asked, which is, for other models of codes, like the repetition code and the toric code, I know how to think about these as physical phases of matter. Okay, so with these models were, as I said, they were written by computer scientists. If you read the papers, they just go kind of theorem proof, theorem proof. There's some constructions of expander graphs, and then they prove some properties of rate and distance. And there's very little physical intuition in those papers. So for the last few years, this thing is cutting my title. Okay, yeah, for the last few years, the question that I've been asking largely with Tibor has been, what is the physics of these novel LDPC codes? Okay, can we think of them in the language of gauge theories? Can we think about phases of matter that we're familiar with? For instance, quantum topological codes, symmetry protected topological phases, symmetry breaking phases. Can I sharply formulate all of these phases on these non-trivial geometries? And do these codes correspond to some kind of topological phase? Okay, and the answer turns out to be yes. These models will also, they're topological in the sense that, again, the ground states are locally indistinguishable, okay? But then, sort of like fractons, they're not topological in that the ground state degeneracy scales with system size, okay? And okay. Yeah, but there is a topological feature to these models, and I'm going to tell you about how we think of them as glasses. So it's kind of weird because there's a sense in which these models are both spin liquids because they're locally indistinguishable, and they're spin glasses. So okay, I don't know what to call that. Okay, and then you can ask, do these models correspond to stable phases? Okay, to have a stable phase, I'd want things like the ground state degeneracy to be stable as I add perturbations. I would want some properties of the ground states to be kind of continuously connected to each other. So, if I really want to think about the physics of these models, can I think of it as a phase, or is it kind of some kind of isolated point in parameter space? Okay, and in these papers here, we were actually able to, this was by my group, this was by another group, we were actually able to prove that these LDPC codes correspond to stable phases of matter. And this is, at the outset, really weird, okay? Because remember that the code rate k is proportional to n in these models. If the code rate k is proportional to n, that means I have exponentially many ground states in system size, which means I have an extensive ground state entropy, okay? There are cases where you can get this kind of extensive ground state entropy, say in frustrated magnets, but there you know that as soon as you add some perturbation, the perturbations lift that degeneracy. Here, because of this topological nature of this phase, I can start with this extensive ground state entropy and I add perturbations to the system, but this degeneracy is maintained. There is a gap and there's these exponentially many states that are stably protected below that gap. So it's very weird from the point of view of something like the third law. Okay, so I'm not gonna, there's a lot of things I could say here. I'm not gonna say those. I'm gonna now move to the thermodynamics and dynamics of these LDPC codes. Okay, so not the codes from the point of view of their equilibrium properties, but the codes from the point of view of their dynamical properties. And the feature that I'm going to focus on when I'm going to talk about dynamics is a particular process called a quantum memory. Okay, I've already alluded to this a few times, but a memory, okay, is an action which preserves the code space. Okay, so this is fundamentally a non-ergodic dynamical process. Okay, if you have in mind your system, you've encoded some information in your code states. Now you're going to have noise, okay, that's coming in, and the noise is fundamentally trying to make excitations, and this is going to try to take you out of the code space. The code space is there's no excitations. All the vertex terms are happy, all the plaquette terms are happy. There are no charges, there are no vortices, but these errors make those types of excitations. Okay, so if you allow those errors to explore all the state space available, okay, then you're going to leave your code space very rapidly. Okay, so memory means you want to keep your system in that ground space. Okay, so that's fundamentally non-ergodic. And there's two kind of standard mechanisms for achieving this kind of memory. Okay, the first is what's called active error correction. This is the type of process that Google is building in its lab. Okay, so here we have in mind some noisy chip. Okay, you have errors, and the errors make all sorts of excitations in your system. You go in and you make some classical measurements. You can go in and you can measure these operators, these star and plaquette operators, to deduce where these errors are. Then you do some processing of this measurement data on your classical computer and decide what's the corrective feedback operation that I should act with to pair up all these errors and come back to the code space. Okay, because because the excitations are deconfined in this model, once created, they can actually wander off quite far from each other. So in order to preserve this memory, okay, you may need to act with a correction operator, which is quite non-local. Okay, so in this case, you have to constantly do this process of making measurements, applying feedback, and this is an active feedback process. And you can think of this as protecting information by processing information. Okay, you're removing entropy from the system every time you make measurements and do feedback. The much simpler way to protect memory is passively. Okay, and this is you're protecting information via thermally stable order. Okay, so imagine that you had your system topological order, symmetry breaking order, and you could just couple it to a cold, you could just maintain it at a cold enough temperature by hooking it up to some kind of fridge, okay, or a bath. And then as long as you leave it there at that low temperature, suppose you could say that memory is going to be maintained as long as you maintain that low enough temperature, okay? That would be great. Okay, then you wouldn't have to keep doing this kind of active correction step, which can be very expensive. So you can think of this as what you would need in order to make a quantum hard drive. Okay, when you have a magnetic classical hard drive in your system, you just have thermally stable order, which protects it. Okay, yeah. Yeah.
I sympathize with this.
Yeah.
But on the other hand, the advantage of the first approach is that you also have information of how often errors are occurring.
Yes, yes. This is, yes. Okay.
So maybe a mixture is.
Yeah. Okay. So let me expand on the statement of passive memory from thermally stable order for a moment. Okay. Again, let's come back to the simplest classical example, the 2D Ising model. This has a thermodynamic phase transition at Tc. There are two symmetry broken equilibrium states, the mostly up state and the mostly down state, separated by macroscopic free energy barriers. Okay, if you want to be a more formal statistical mechanic, then you'll say that the Gibbs state ceases to be unique below some Tc. These are the two Gibbs states, the up and the down. Okay, and there's there's many ways of defining these Gibbs states. Okay, there's a so-called DLR prescription. There's a Peierls prescription, which is you stick in boundary conditions. You can stick in either up boundary conditions or down boundary conditions, and you look at the state deep in the bulk, and you ask, does it depend on the boundary conditions that you put in there? If it does, then you get these different Gibbs states. Okay, for our talk, for my talk, I want to take a different approach, a more dynamical approach, which relies on the classical bottleneck theorem, because this is where bottlenecks come in. So it's a very, very natural approach, actually. Okay, so let's look at the global Gibbs state of the Ising model, e to the minus beta h. Okay, this is configuration space. It's a cartoon of configuration space. And I ask, where does the Gibbs state, on what types of configurations does the Gibbs state have large weight, below and above TC? Okay, so here I've parameterized the weight in the Gibbs state by the magnetization density of the configurations. So above TC, you're a paramagnet. So, you know, your Gibbs state looks like it has most of its weight and states near zero magnetization. Okay. Below TC, this weight distribution splits off into these macroscopically distinct clusters. You have large weight on this mostly up state, and you have large weight on this mostly down state. Okay. Now, what happens is that if you start in a state that was mostly up, okay, with large magnetization density, and you run some local Glauber dynamics, detailed balance obeying Monte Carlo metropolis dynamics, that's going to try to prepare the global Gibbs state, what will happen is that you prepare the Gibbs state in this component very quickly, but then because you have to go through this bottleneck region where there's very, very low weight in the Gibbs state, in order to go from mostly up to mostly down, you actually remain stuck in this mostly up state for some diverging lifetime. Okay, in fact, you remain stuck in this mostly up state for a time which goes like e to the square root of n or e to the L, and this gives you a memory. Okay, if I start here, I'm going to stay here in this mostly up state for a time which is diverging exponentially with system size. This can be formalized using this Markov chain bottleneck theorem. You can look at the weight of the Gibbs state in some region, which you call the shell or the bottleneck, okay? And you can look at the ratio weights in the bottleneck and the bottle. The bottle is the main component. This actually formally defines for you a free energy barrier, okay? And then when that free energy barrier is diverging, that sets a lifetime, which goes as the inverse of how that free energy barrier diverges for being able to preserve memory, okay? So to summarize, for the classical context, okay, let's actually put them, yes, for the classical context, if I chose to use the 1D Ising model or repetition code for my memory, okay, then I would have to do active error correction, because again, there's no finite temperature ordered phase. You have point-like excitations, point-like domain walls, these are deconfined. On the other hand, if I use the 2D Ising model, then my excitations are loop-like, they're extended, and there is a finite temperature ordered phase, and I can do passive error correction. Likewise, if I try to do this for quantum, if I work with the two-dimensional toric code, I need at least 2 dimensions to talk about quantum, then my excitations are point-like, they're deconfined, there's no topological order at finite temperature. On the other hand, if I want my excitations, which in this case are electric and magnetic fluxes, to form closed loops, for them to be extended objects, to get thermally stable topological order, it turns out I actually need to go to 4 dimensions. Okay, the 4-dimensional toric code will do it. There's no example known in 3 dimensions or less. Okay, and these models are actually very closely connected to each other. Remember, I was telling you about these product constructions to build quantum codes out of classical codes. It turns out that you can build the toric code out of 2 1D Ising models. So the fact that the excitations in the toric code are deconfined is directly inherited from these deconfined domain walls of the 1D Ising model. So there's a very, very deep relationship between these 1D Ising models and the 2D toric code, and between the 2D Ising model and the 4D toric code, and thinking about these classical models basically gets you most of the way there in thinking about memory in these quantum models. Okay, so
May I just ask,
yeah.
is there a reason why there isn't one in 3D, or we just don't know one yet?
Well, okay, so we don't know one. The simple reason is that for the 2D model, you have charges to get a thermally stable topological phase. We need both the X and the Z sectors to be robust. For the toric code, you have point-like charges and point-like vortices. They're both deconfined. When I go to 3 dimensions, I can make my magnetic flux loops loop-like, but my charges are still point-like. And then the charges will be deconfined, but my fluxes can be confined. So then I get a stable classical memory, but not a stable quantum memory. To get a stable quantum memory, I need both the charges and the fluxes to form vortex loops, to be loop-like. And there, the simplest way to do it is 4D. All of this work on fractons was motivated by trying to search for something in 3D. It didn't quite work. So, okay, but it's still an open question. There's no proof that it can't happen in 3D. Yeah.
Question. When we take the 2D
Yeah.
2D Kitaev model and
Yes.
we take it to its gapped phase, we get the toric code.
Correct.
So is that a strategy for higher dimensions, taking 3D or 4D Kitaev models and taking them to their gapless phases? Would they, or do they fail?
No, I think yeah. So this is the toric code is the gapped topological phase of the Kitaev honeycomb model in 2D.
If I give you a 3D or a 4D Kitaev
Yes.
model, which certainly exists, and I drive it to its gapped phase,
Yes.
will I have a higher dimensional toric code?
Oh, I don't know what the phase diagram of that looks
I
like.
see.
Yeah, but the 3D toric code is gapped and certainly exists. It's like 3D gauge theory, 3D lattice gauge theory, likewise with 4D. So it's just a question of, does the higher dimensional Kitaev model host that same phase in its gapped phase? And I don't know. It seems likely,
Yeah.
but I don't know. Yeah. Okay. Okay. So upshot, the main mechanism that people know, that people talk about to get a quantum memory is thermally stable topological order. That's what a quantum hard drive might look like. And this exists in 4 dimensions or higher. Okay. Now I want to present a puzzle. Okay. And then the resolution to the puzzle. Uh-oh, it's totally blocked. Okay. The puzzle is that in these LDPC codes that I told you about, there is passive memory. Okay? There are known robust passive decoders. Okay, these you just couple something up, do local dynamics. These models are known to have robust passive memories. On the other hand, if you look at the partition functions of these models, or if you look at these models, naively, they have no finite temperature ordered phase. Okay, one way to see that is that these models have all the checks in these models, all the terms in these models, in these particular types of models, are completely independent from each other. Okay, which means there's no product of checks. Like in an Ising model, I take 4 checks around a plaquette and I get 1. In these models, that's not true. So every check can kind of be independently excited. So my excitations are point-like. And this means I can do a very simple Kramer's Wannier transformation, and I can write the Hamiltonian purely in terms of these independent check degrees of freedom. In general, this is some non-local transformation, but let's not worry about that. And once you do this transformation, then because each of these checks tau is independent, your partition function just looks like the partition function of a decoupled paramagnet, okay, but with some large number of some 2 to the k overall factor coming from these code words or the symmetry operators. Okay, so this is a completely analytic, simple partition function. So these models have this type of robust passive memory, but their thermodynamics by this measure looks trivial. Okay, so so how do we understand this? Okay, and actually now we can go back in history and think about how this might work for classical models. And in classical models, well, it turns out there is another route to passive memory, which isn't just the 2D Ising model, and that other route is spin glass order, right? So when you think of a spin glass, the first picture that might come to your mind is some kind of complex, rugged, free energy landscape. To what extent this landscape is true for local models is a question of much debate, but it is known that in certain non-local all-to-all models like the Sherrington-Kirkpatrick models, this picture is established, and these landscapes host multiple, you can look at the bottom of the landscape, there's some spin configuration there, okay? And now these local minima, the global minima, are all associated with equilibrium states, okay, with some diverging lifetime. And the glass transition, okay, below which we get these many, many different equilibrium states, need not be accompanied by any thermodynamic transition. Because this is a dynamical phenomena, the thermodynamics could look completely trivial, okay? So, and this is very, very different from spontaneous symmetry breaking, because all of these minima, in the Ising model, I had the all up and the all down as my two minima, which hosted my Gibbs states, but those were related by the action of an Ising symmetry. Here I have these many local minima, and they need not be related by the action of any symmetries in the problem. I have these 2 to the k symmetries, but these need not relate any of these states. And most of them are not going to be related by that. Yeah. Okay.
What exactly was puzzling about this?
Well, what was puzzling is you have a passive memory. Okay. A passive memory is something that means that you can do local Monte Carlo dynamics on your computer and it works. Usually, when people have passive memory and they ask about how did I get this passive memory, it's usually associated with thermally stable topological order or thermally stable symmetry breaking order, like in the 2D Ising model or the 4D toric code. In this model, if you just look at the partition function of the model, then it's perfectly analytic. There's no TC. If you compute some thermodynamic function from the partition function, it'll look like what you would get for decoupled paramagnets. No. So this is for an LDPC code.
No, what you're stating is that there's a well-known partition function for that particular code. Okay.
For any code that has no redundancies. And many of these LDPC codes can be shown to have no redundancies. Yeah.
And so you're saying that the way out of this is to advance the state?
Well, so the way out of this is like, so as I said, we were trying to understand what's the physical picture. So the physical picture is now that like, yes, this is consistent, but the way it's consistent with your physical phenomena is that the phase that will correspond to this LDPC code is not a simple thermally stable topological order, but a topological class. Okay, good. All right, so this is how we get memory from classical spin glasses. Okay, we have this rugged free energy landscape, lots and lots of wells, each well associated with some state. Okay, in this bottleneck theorem picture, you can think of every one of these wells define some region of configuration space, which is surrounded by a bottleneck, because to escape this region, you have to go through some big barrier. Okay, yeah.
Sorry, this is probably me not missing the idea, but to have a memory, you need to be able to encode things. And for that, you need to know which states you are encoding it in. Whereas here, maybe you don't know this.
Okay, good. So that's a separate question about how do you actually, so that was like Hopfield memory is like, how do I actually design a JIJ matrix that will put the desired configurations at the bottoms of the well. Let me not worry about that right now. These models are actually, they're called linear codes, they're XOR SAT problems. So they're actually very easy to get a basis for the code words is actually very easy. You just have a kernel of some matrix. It's a polynomial time problem. So you can actually find a basis for all of these code words, and then you just decide you're going to use them. Okay, but this is not an inverse design problem. Yeah. Okay. Good. So in this bottleneck picture, each of these wells can be thought of as hosting these bottles surrounded by these bottlenecks. And then, the definition of spin glass order that one could propose is captured by these 2 features, one which I call shattering, and the other which I call incongruence. I guess I'm not the first, I'm not calling them that, that's what they're called. Shattering means that there are exponentially many Gibbs state components, which are not going to be related to each other by just symmetries of the problem. Each of these Gibbs states components is only going to carry some exponentially small amount of weight. And if you start in one of these components, you're going to stay there for some diverging lifetime. Okay, that's what shattering means, that your whole configuration space is going to fragment into these exponential pieces. And incongruence means that most of these Gibbs state components don't locally look like ground states anywhere. So this is some language from Fisher and Hughes. Okay, so most of these ground states only contain finite energy density states. They don't locally look like ground states anywhere. So now any steady state of local detail balance obeying Markov dynamics, this forms a convex set. It can be written in this following way. Here are the components. These are my extremal states, and the components can have some weights. Okay, I can prepare a state with those weights on these different components. And this state is going to basically be a steady state. So a vector, a classical vector, which includes those numbers, is going to be preserved. Okay, so that's why this encodes k bits. You can also characterize the landscape by looking at the configurational entropy. If I take the Gibbs state and I write it in terms of all of these components, then you'll see it has all these components with some weights. If it was an Ising model, these weights would just be 1/2 and 1/2. But now each of these weights is something exponentially small. I can write an entropy from these weights using some W log W, like I can write the Shannon entropy of this distribution over these components. And then spin glass order means that shattering would tell you that this has some finite entropy density and that this entropy density is increasing with temperature. Okay, so you have many, many components, all of which are going up. And as I said, these components can be used to encode logical bits, okay, because you can park something at the bottom of these wells, and as long as there's some thermal noise, then you'll stay there, okay? So the question is, can we encode quantum memory in a similar way, okay? Usually when people talk about quantum spin glasses, they have in mind this classical spin glass and sticking some kind of transverse field on it, which can cause tunneling between these different wells. But remember, the ground states of the toric code are highly entangled, locally indistinguishable. Those don't look like the ground states of a 2D transverse field Ising model. So I can't start from an Ising model, stick in a field, and declare a quantum memory. I need to make something entangled and topological. Okay, so that's the question. Can I have that? And the reason I'm giving it this talk is that yes, okay. So now when we put it all together, there's two ways to encode classical memory passively. We have spontaneous symmetry breaking and we have spin glass order.
Can I just ask for?
Yeah.
And misremembering.
Mm.
In spin glass theory, you can make it look like symmetry breaking with the replica. And then you get replica symmetry.
You have replica symmetry breaking, yes.
So all the
Oh, like, do you know what replica symmetry is? Like it's some n replicas and some limit n going to 0. Like it's not a symmetry of the problem.
No,
Right?
it's fake. It's a way of making spin glass order look a bit like the.
In some very mathematical way. I don't even know if people who work on replica symmetry breaking are going to tell you that replica symmetry breaking looks like symmetry breaking. Like it's a mathematical tool, yes. But okay.
As are all things in physics in the early days,
Yeah.
Miles didn't believe antiferromagnetism was real, even though he thought it was a mathematical invention.
I see. No, I'm not saying it's not real. I think for like Sherrington Kirkpatrick, it's proven to be true. It's just you have n replicas and then you take a limit, n goes to 0. I don't know how to think, like, well, that's not a symmetry of the Hamiltonian. I don't know. Like,
There
yeah.
are ways that are these time extensive for the slightly activity that people look at, which again is another way of making it a bit more like a symmetry breaking piece.
I don't know. I mean, it's fine. We now think of topological order as higher form SSB. So I guess I can put here replica SSB. That's fine. I'm happy to do that. You know? So I'm not hung up on that. It's just they at least seem qualitatively different. Okay. All right. Okay, and then for quantum memory, we have topological order and the thermally stable one. So what we're adding is this box, which was left, intentionally left empty. Yeah, just like you can encode classical memory using spin glass order, you can actually also encode quantum memory, but using a different type of spin glass order, which is this topological spin glass order. So let me define this and then stop and not tell you any details because it's not going to be, I'm already far out of time, but okay. So let me just define the phase for you at least. Okay, to define the phase, it's going to have 4 features, okay? So this is a picture you should have in mind. As I said, there's 2 to the k symmetry sectors. There's 2 to the k ground states. There's 2 to the k symmetry operators. So whatever landscape picture or whatever spectrum picture I draw has to get repeated 2 to the k times, okay? So in a way, this is already sort of unusual because k is order n. So I kind of get 2 to the k or 2 to the n symmetry related ground states kind of for free, okay? That's fine. Now, shattering means, as I said, there's exponentially many stable minima in each symmetry sector, okay? And incongruence means there's many, many more stable minima at finite temperatures. So these two together characterize the classical complexity of the free energy landscape. These are shared between classical and quantum glasses. The topological feature is going to be that if you look at each minimum and you look at the portion of Hilbert space associated with that minimum, okay, this minimum is a component, okay, in Gibbs state. It has weight on some subspace of Hilbert space. And now that subspace is a Gibbs state, okay, defines a mixed state on that subspace. You can ask, what does it mean for a mixed state to be long range entangled or to have entanglement, which is non-trivial? This is a question that is actually quite open. One way that you can define it due to Hastings is that if you have some mixed state, there's many different decompositions of the mixed state in terms of pure states, okay? And the question is there a decomposition which can be purely in terms of short-range entangled pure states? A short-range entangled pure state is one where you can start with a product state, run some finite depth circuit or some finite time local evolution, and a state that you obtain in that way is what we call a short-range entangled state. And for the Gibbs state to have long-range entanglement, what you mean is that it cannot be written in terms of this short-range entangled decomposition, okay? And then you can use these wells in these different symmetry-related states, the dark blue wells or the light blue wells, and you can use those to embed quantum memory, much like you can use the states of the toric code to encode these qubits defining the X and Z logical states. Okay, so there's many, many emergent quantum memories, including at using these finite temperature wells. So there's entanglement at finite temperature, there's memory at finite temperature. Okay, so you put those together, those are the features that will define the topological spin glass. And what's pretty remarkable is that we can actually prove, like this is one of the first papers I've written, which has a theorem in the paper, and you can prove that this phase exists using proof methods and techniques from coding theory. Okay, so this is how it kind of fits together. It actually turns out that classical LDPC codes display classical spin glass order, and quantum LDPC codes built out of products of these display this kind of topological quantum spin glass order. Okay, let me make a few comments. Okay, the methods in these models, okay, I'm talking about Hamiltonians, which are defined by these checks. Okay, all the checks are happy. So there's no disorder in these models. Okay, usually when we think about glasses, we think about disordered models. Here, there's no disorder whatsoever. And as we were discussing when we were talking about these expander graphs, we can actually talk about these models also on geometries which are not disordered. Okay, so these random regular graphs, at least there's disorder in the graph, but you can also have these explicit expander graph constructions. So there's no disorder. There's no conventional frustration because the model has many, many ground states. Okay, so it's not hard to find ground states. And the graphs need not be locally tree-like. Actually, in the spin glass literature, there's been some work on talking about spin glasses without disorder using the cavity method. But for those, you usually have in mind some locally tree-like geometry, and the locally tree-like geometry ends up giving you some approximate analytic methods, but we don't need to do that. Okay, so this adds to the family of known spin glasses, even classically, and because there's no disorder, no frustration, this might furnish some insight into structural glasses, okay, maybe. Then our method of analysis is rigorous. We can prove spin glass order and derive various features of the structure of energy barriers just using properties of codes, something called linear confinement and this bottleneck theorem. Such rigorous results are pretty hard to come by, even in well-studied classical spin glasses. And more importantly, this is at least much more transparent. At least I find it much more transparent than replica symmetry breaking. Okay, so I should probably stop and not keep going unless you want me to keep going.
I think it'd be great to stop for some questions.
Okay.
There's lots of questions coming up.
Yeah, okay. I'll stop for some questions and
Yeah,
then.
thank you very much.
Okay.
Lots of great ideas here, so let's open it up. Yeah, look.
So Okay, so you have like this diagram on the slide where you have like classical expander.
Mhm.
Okay, classical spin class from that.
Yes. So if you have a classical expander graph, like not every expander graph is going to give you a spin glass, but depending on, you can arrange things on, so you start with an expander graph, you put some generalized Ising model on it, that can give you a classical spin glass. In fact, a very standard model of LDPC codes called, didn't get to talk about, called Gallagher codes, is very, very closely related to some models called diluted P spin glasses, which have been studied in the spin glass literature.
So it's not disordered.
It's not disordered.
It's a long range, right?
No. So it's okay. Since you asked, I'm gonna.
The concept of spin glasses without disorder has certainly been discussed.
Yes, yes.
Quite extensively.
Yes, yes. And that's my slide here, which is where. Okay, good. So this is how it fits into what people have talked about in spin glasses. There's the standard Edwards-Anderson model. This is spatially local random interactions. There's some JIJ, okay, finite bit and check degree. This is analytically intractable. There's many open questions even after decades of study. Then there's it's p-body vertex interactions, but notice that all these colors are blue, which means there's no disorder. The J is out front. Okay, so this was studied by Mazard and collaborators in 2001, and they showed that this model does have one-step replica symmetry breaking and spin glass order. But for them the geometry was random, but actually I don't think that's so important. Like they could have done it even without random geometry. What they used was this cavity method, okay, and related it to one-step replica symmetry breaking. So what they do need to be able to run these methods is for the geometry to be locally tree-like. Okay, so they have these long loops, these cavity methods, belief propagation, survey propagation. You start from the leaves, you come in. That works well. That works exactly on a tree-like graph. The whole business of one-step replica symmetry breaking is to treat these long loops in some way. That gives you some approximations. Okay. But you can do it. And in fact, what we add to this family of models is a completely orthogonal way, not having to do with cavity method or replica symmetry breaking, to derive spin glass order in this family of models, using this coding method, which I think is it's like one page of algebra versus like pages and pages of replica calculations, very physical. And then the method that we use doesn't require this to be locally tree-like. So we can, the kind of hyperbolic tessellation, that method is totally general. So I don't need to, so it adds to the classical literature in that context, that it doesn't need to be locally tree-like. Yeah.
So I think for a very interesting talk. Sorry if I understand, but in the quantum topological, so this topological quantum spin glass, this like sigma of like the business volume has to be toric code E, and they have to interact together.
Yeah. So this is all classical.
Right.
Yeah.
So what kind of things in toric code can I mean, to like imagine how to implement that like experimentally? Then like what kind of interactions do we have to?
Okay, good. Yeah. So oh dear. So look, so in the toric code, your interactions are four-body. Okay. The simplest models that we can, so the proofs of these models require degrees in the hundreds and interactions in the hundreds, but order one. Okay. We ran numerics for much simpler models. So we worked with these degree 7 classical models. Okay. Provably, these are beyond the proofs, but it just works beautifully. Okay. So this is a degree 7 graph where on every vertex you put in what's called a small Hamming code. Okay. So now a Hamming code, this is classical still. It's 4-body classical interactions, and it's 3 sets of 4-body interactions on every vertex. Okay. So this is the classical model. And now, as I was saying, you can make this product construction from this classical model. This is, you turn a crank, which allows you to take 1D Ising models and spit out the toric code. I apply that crank to this model that I just showed you, okay, either on a hyperbolic geometry or in this tree-like geometry. That automatically gives you this toric code. So it's going to be something which lives on this crazy geometry. and it's going to involve few body. Okay, so now I go from 4 body checks to, I think it was like, I don't know, maybe 10 or something. Okay, but that's what it looks like. It's a set of rules, you can write it, and on these quantum simulators where you can program graphs and you can, it's still very challenging. That's why, no one's done it yet. In principle, you might be able to just, like when you do a toric code in a quantum simulator, you're actually going in and measuring the checks. You're not like making a Hamiltonian. So likewise here, you would go in and you'd have to measure 10 body checks instead of 4 body checks. But okay, it's just some circuit you would run and you can run it.
Yeah, good.
Just a qualitative question about sort of size of this family of quantum probes.
Yes.
So how strongly constrained are the rules and how many different ones?
Oh, it's huge actually. So what I need, okay, good. Okay, so let's go back. There's a feature that I use to derive the spin glass order. There's a physical feature, and it's the key physical feature. Okay, and that physical feature is a property called confinement or expansion. Again, all of this is cut out. That should say key ingredient, linear confinement in classical expander codes. Okay, so what linear confinement tells you is that if you start in a code word and you start flipping spins or making errors, as long as the number of spins that you flip is less than some extensive fraction of the total number of spins, your energy cost, the energy cost that you pay, has to grow by an amount that is proportional to the number of spins flipped. So it's an extensive linear energy barrier. Okay, this inherently comes from this expander geometry where you start making defects and they have to keep proliferating. They can't cancel each other until your graph closes. And this is very unusual if you're used to thinking about these types of Euclidean geometries where bulk to boundary ratios scale not proportionally. So your energy costs are sublinear. Once you give me linear energy barriers around code words, I'm good to go. Okay, like I can derive the energy landscape for you with 1 page of algebra. That's it. Okay, so that's why this is so much more transparent compared to the other models. We're basically saying that the energy landscape will provably have many, many local minima surrounded by these barriers, and they will host bottlenecks. Now, when I try to come to quantum codes, the condition that I need is that this coefficient here, the slope of this barrier, is steep enough. Okay, because if these were very shallow wells, then you can imagine that the wells start merging with each other. Okay, so I need there to be few redundancies. Okay, because I want to be able to say that, like, look, I can violate 1 check. Okay, and that's going to be a very, very different configuration. Okay, that can be pretty far. And I need this to be steep enough. Okay, and that's more or less it. Yeah, and the other really remarkable thing about quantum codes actually is that in the classical codes, I have these extensive barriers, right? So you can say an extensive energy barrier, well, it'll give me an extensive free energy barrier because entropy can be at most order n. So fine, that's kind of, it's amazing that we can do it. And in fact, this is the picture for these diluted p-spin glasses, which doesn't require you to go down 1 step RSB, okay? But then in the quantum models, it actually turns out that when you take these products, you can shrink the effective barrier. Okay, the effective barrier it's still linear, but it may only extend to square root of n. So then you can't just do this naive calculation of like extensive energy goes to extensive free energy, but it actually still works. And we were able to show that it works for any, as long as this barrier is only as big as log, you can get a memory time. So, okay, so that's the main kind of structure that we needed, this energy barrier. And if you have that, then it works. Provably, you don't have that in so many models, but in practice, you have that in many models. We just did the simplest code we could do, and it all worked, okay, and numerically. So, yeah.
Okay. Any last questions to Vedika? Well, let's thank her for a great talk. Before we end today, first of all, for those of you going to Seamus's public talk at we're going to be making our way over there.
Mm.
Probably, but we don't need to get there till about 6:30. So
Yeah.
So I think I invite everyone to make their own way across to King's Cross. It's not very far from here. The IOP is labelled on Google Maps. And then tomorrow we're back into the Roberts building.
Yes, but a different lecture theatre. It's floor 4, not floor 5.
A little less walking.
I mean, you just press one button under the elevator for most people.
408.
Yeah.
I see. Okay.
I mean, again, just check the schedule, all the information's there. As long as you know it's somewhere different, you'll look.
Yeah, great. And see you all soon. Public lectures at the IOP Institute of Physics. It's just near to King's Cross Station. You can type it into your Google.